hiking through the and just so easy. I got it for sure. Just like someone made it like 20 years ago.
Which first?
I go by Louis.
Okay, Louis. Okay.
Aaron's my real name. Somehow I go by Louis.
Okay, so let's start with the final talk of the morning session. Again, about hypergraph sparsification is by, and I'm not sure, Aaron or Louis. Come on.
All right. So thanks for the introduction, and thanks to everyone for hosting the workshop, and I guess Sanjeev for inviting me. So again, yeah, we'll be talking about hypergraph sparsification, and we will see a lot of the same citations that we saw before, but hopefully some new ideas as a result. And this is based on joint work with Sanjeev and Madhu, like the other paper too. So the starting point, again, will be the same as what we saw, but it's going to be like the starting point will be the cut sparsification of graphs. The way this works is you're given a graph G with vertices V and edges E, and we'll be looking at cuts corresponding to subsets S of the vertices. The way this works is for some subset S, the set of cut edges will be exactly those edges in G with one endpoint in S and one endpoint in V minus S. So they're basically just the edges crossing the cut. And using this, we can define like the size of a cut just to be the weight of the edges that are crossing. And with this, you can then define a cut sparsifier to be a reweighted subgraph, such that on every single cut, the weight of these cut edges is preserved to a multiplicative factor. And it turns out in the 90s, there was a seminal line of work by Karger and then ultimately Bencher and Karger, where they established that every graph on n vertices admits one of these 1 plus or minus epsilon cut sparsifiers, where the number of edges that's preserved is near linear in the number of vertices. It turns out because of this like wide appeal of the notion of cut sparsification in graphs, a natural follow-up question was to study the ability to sparsify hypergraphs while still preserving their cuts. This was ultimately studied, again, starting in the 2010s by Roby in this Kogan-Krauthammer paper, but ultimately settled by this paper with you. I don't know if he's here right now, but then Sanjeev and Ansh as well. And here they showed that every hypergraph on n vertices admits a 1 plus or minus epsilon cut sparsifier, where the number of hyperedges now is, again, near linear in the number of vertices. So one thing to note, though, also is our definition of a hyperedge being cut here will correspond to this like all or nothing function that Roby mentioned in his talk. All that means is that a hyperedge is cut by one of these sets S if it has at least one vertex on inside S and at least one vertex in V minus S. So kind of like the standard definition analogous to the graph setting. But one kind of pitfall of a lot of these algorithms, as in like the CKN20 paper for computing these cut sparsifiers of hypergraphs, is that they relied on a very strong notion of access to the hypergraph. So in particular, they were using like repeated complete access to all of the hyperedges in the hypergraph when computing sampling rates. And this means that in very many natural computational settings, such as like streaming algorithms or this MPC model, these kind of algorithms don't translate into anything too meaningful. So today, the goal will hopefully be to understand the possibility of constructing these hypergraph cut sparsifiers in more restricted computational settings. And in particular, the focus today will be in the linear sketching setting. And the reason why is because it leads to very canonical algorithms in both dynamic streaming and that's like massively parallel computation model. And for those of you who are unfamiliar, the definition of a linear sketch is just that we have some kind of measurement matrix, which we apply to the hypergraph. And the way we represent the hypergraph is just as like a 0, 1 valued vector, where there's a single coordinate for each hyperedge. So the presence of a hyperedge means that a coordinate will be 1. The absence is just a 0 in that coordinate. And like our specific question will be like the optimal bit complexity of a linear sketch, which can be used to recover a 1 plus or minus epsilon cut sparsifier of a hypergraph. And I didn't put it there, but everything will be with high probability. If things become deterministic, the space bounds aren't really too interesting. So as a starting point, it turns out this question was originally studied in the graph setting in the 2010s. Like a really nice line of work by Anguha and then Andrew showed that if you want to construct cut sparsifiers of a graph, you can actually do this with just like O tilde n over epsilon squared bits. And as mentioned before, this leads to very nice algorithms for creating sparsifiers in like dynamic streams and for like this MPC model. A building block that appeared in this sequence of works and a building block that we will use today is the notion of an L0 sampler. And the key property about these L0 samplers that we'll use is, well, A, that you can implement an L0 sampler with a linear sketch, and B, that they return a random index. Right? They're given a vector x of length u, where some coordinates may be 0 and some coordinates may be non-zero. And they return a uniformly random index among the like non-zero support of the vector. So they return a random index I such that xi is non-zero, along with the value of this coordinate xi. And so the sequence of works in 2012 by the AGM authors show that there's an almost like canonical way to create L0 samplers for like the adjacency lists of a vertex, such that when you open this L0 sampler, when you recover from this L0 sampler, it gives you like the exact description of an edge which is incident to this vertex. Okay, so that's very nice. But even more important than this is when you're given like a subset C of vertices, like some component of vertices, you can actually add together the L0 samplers for the constituent vertices, and it'll become an L0 sampler for the neighborhood of this entire component. So that's to say, all the interior edges cancel out when you add these L0 samplers together, and all you're left with is the edges that are leaving this component. And the one caveat here is that you have to use the same randomness. You can't just add arbitrary linear sketches. They have to be initialized like with the same randomness if you want to add them. And it turns out that using this kind of property, you can actually create spanning forests just in order like n log n L0 samplers. It's a very nice iterative procedure. In the first round, every vertex like recovers a constituent edge, and now you just merge all of these edges together. So if you like, vertex u and v were connected, just add their samplers together, and now you'll sample a new edge that's leaving u and v. And you just repeat this log n times. So the next thing we have to understand is how do we actually build graph sparsifiers? So far, all we're talking about is L0 samplers, spanning forests. How do we actually turn this into a mechanism for creating graph sparsifiers? And the reason I'm talking about this is because when we go to the hypergraph setting, this will be like a very valuable intuition for like how exactly we should build a hypergraph sparsification algorithm. And it turns out there's actually a pretty simple iterative procedure. And I promise it's simple, even though it might look a little messy right now. And this is kind of dating back to the work of Bencher and Karger in '96, but it's appeared in various places throughout the years. And so for now, let's ignore that there's like this loop right here going for 2 log n iterations. And let's just imagine a single iteration of this procedure. We're starting with the graph G, and G0 equals G. So let's just start with this graph G. And now there's this notion of strength that comes to this, basically dates back to this work of Karger in 1993. And we have some property which says if every edge in the graph has high strength, and here high just means some constant times log n, and like, you can ignore epsilon for now, basically. If every edge is high strength, then you can afford to sample every edge at rate 1/2, give it weight 2 if it survives, and this will be a cut-sparsifier with high probability. Right, so all we're going to do, in this first iteration, we have the graph G0. So let F0 be all these low-strength edges. These are the ones where we can't afford to sample. And just keep these exactly as they are. All the remaining edges, right, because we remove the things with low strength, all the remaining edges have high strength. And now we can afford to sample at rate 1/2. So what this might look like, if this was our graph G0, we have kind of this dumbbell graph with 2 cliques. The only edge with low strength will be this edge crossing in the middle. So we recover this edge, and then we sample everything else at rate 1/2. Right, and now we're just doing this for many iterations. So now we get some set of 2 graphs, which are a sparsifier for the original graph. And now we just recurse on this graph G1 that we get. Right, so G1 is G0 minus F0 sampled at rate 1/2. And now just repeat the same procedure for G1. And so are there any questions on this? Because this will like appear throughout the talk, so it would be great if anyone wants anything to clarify. OK, perfect. So this is the statement of the algorithm again. One remark I want to say, so on the previous slide, I was actually saying that this epsilon was just use the same epsilon. A slight subtlety that might arise is that you're actually kind of computing a sparsifier of a sparsifier. So the error is accumulating in each round. Right? So in the first round, sure, we get a 1 plus or minus epsilon sparsifier. But then we're computing like in the I equals 1 iteration, we're getting a 1 plus or minus epsilon of a 1 plus or minus epsilon. So if you really want to just cover all our bases, we can set some epsilon prime, which is just epsilon over some log n. And then this way, the actual accuracy of the sparsifier we get doesn't degrade too much. The final details that, OK, here I was saying, OK, recover all these edges of low strength. It's not exactly clear like how to do this with a linear sketch. Instead, we take advantage of the fact that you don't actually have to recover these exactly. You just have to recover like a superset of these low strength edges. And it turns out that if you store some like polylog n disjoint spanning forests, this recovers all the low strength edges. So that's all we're going to do. You saw before, we can make this linear sketch for spanning forests. Let's store different copies of them with different randomness. We can like pretty easily enforce this disjointness condition. So all we do, instead of saying fi is these low strength edges, fi will just be like the set of disjoint spanning forests. And now we can tally up like all the spaces that's happening. So we have a log n, just because of running this log n times, we need to store sketch at each of these levels. Number of forests in each level will be something like this log squared n over epsilon squared, or really epsilon prime squared. The number of L0 samplers for each forest is order n log n. And then finally, the number of bits in each L0 sampler will be log cubed n. All that's to say that this will just give you this like O tilde n over epsilon squared algorithm in a very elegant way, and hopefully that is clear to everyone. But OK, this is just working in the graph setting. And as we've seen kind of throughout this week, in general, the hypergraph setting is much more complex than the graph setting. So it's natural to ask, can we generalize this to hypergraphs? In particular, can we like get anything meaningful in the setting of hypergraphs? And just as a note, I'll be talking about several parameters today. So n will always be the size of the vertex set. M will be an upper bound on the number of edges that are present in the hypergraph. And R will be an upper bound on like the size of any particular hyperedge. And I usually refer to this as the arity of the hypergraph. And it turns out, so this was already a question that was asked in 2015, first with Roby's paper, and then in a subsequent paper, also with Andrew, where they showed that a very similar procedure can actually give you like a linear sketch which computes a sparsifier of a hypergraph. So in particular, there are two things that we should note that are different from the previous version of the algorithm. First, we've replaced the 2 log n with a log m. Right? So the reason we chose 2 log n is that the number of edges is like n squared. So if we sample at rate 1/2, 2 log n times, then everything's been recovered. Like there's no more edges under consideration. Here, the number of potential hyperedges is like m. So we have to sample at this rate 1/2 log m times. The second thing to note is that the number of disjoint spanning forests that we store is actually a factor of r larger. And it turns out that this will be very important when it comes to like analyzing the total bit complexity. So the total bit complexity will end up being this kind of O tilde nr squared log to the 4m over epsilon squared. And now let's look at where exactly this complexity is coming from. So first, there's 1 log m just from the fact that there's log m iterations of this entire procedure. At each level, right, we're storing this like disjoint spanning forest kind of linear sketch. And we're storing r of these sketches. Each one requires like n log n L0 samplers. So the total amount of L0 samplers in each level will be some like O tilde nr over this epsilon prime squared, where epsilon prime will now have to be epsilon over log m to again account for this degradation of the accuracy. Finally, because we're working over kind of a larger universe size, the actual size of each individual L0 sampler will scale with that. So before it was just some polylog n. It turns out that when r is arbitrary, the right dependence will be something like r times log m, and then some like dependence on 1 over delta, where delta is like some failure probability. But for our purposes, we'll just call it O tilde r log m. So this total space usage is fine when r is constant, right? When r is constant, m is also bounded by some polynomial in n. And this was really the observation that was made in this GMT 15 paper. It was really to say, for constant arity hypergraphs, everything in the graph setting translates pretty well. We can get these linear sketches with essentially like optimal bit complexity. But today we'll be interested in what happens when we kind of increase the size of these hyperedges and the number of hyperedges in the hypergraph. In particular, when this arity r approaches n, you can also have m being 2 to the omega n. This total bit complexity would be like n to the 7 over epsilon squared. And it's a natural question to then ask, what is the right dependence on r and log m? And recall in the static setting, because of these work CK and 20, and then a long line of work in the spectral setting, we have a pretty good understanding of what the actual bit complexity of a sparsifier is. And in particular, it looks something like nr over epsilon squared. So first of all, there's no dependence on log m that appears here. And there's only a linear dependence on r that appears here. So our question that we're asking today is whether we can match this. And it turns out we can match it in some senses, but not in others. In particular, we get tight like matching, essentially, up to this epsilon squared, upper and lower bounds. So we have a linear dependence on R, a linear dependence on N, and then we do have a logarithmic dependence on M. And this is matched in the lower bound. So one way to interpret this is that if the total number of hyperedges in the hypergraph is just polynomial in N, then we're essentially matching the optimal bit complexity of like a static sparsifier. So you kind of get this like dynamism or like linear property for free. But necessarily, as you scale the number of hyperedges, like you get like a larger and larger dependence on this log M term. And are there any questions, by the way? Let me know if anything is unclear. And yeah, the other key thing to note is that we get the right dependence on R. So in particular, on the previous slide, we saw that the right in the static setting, there was this theta and R. So we are matching the R, and that's kind of a nice qualitative result. And it turns out a lot of the work in the paper goes into optimizing this factor on R. And I think in particular for the rest of the talk today, I'll focus primarily on optimizing this R factor. And then I might mention like 1 or 2 slides on how you can optimize the other factors of the log M. So we can page back to this algorithm we saw for hypergraph sparsification. In particular, recall that we're storing this factor of R disjoint spanning forests. And really, this paper was a bit disadvantaged in the sense that it came out in 2015 before we even knew how to construct hypergraph sparsifiers in the static setting with the optimal dependence on R. Right, so the kind of main issue is that in the KK15 paper, the bit complexity of the sparsifier they get has a quadratic dependence on R. We have the fortune of living in the future where we actually can construct these sparsifiers with the right dependence on R in the static setting. So the question today is whether we can kind of take advantage of some of these more recent works, optimizing the complexity of hypergraph sparsifiers in the static setting, and somehow turn them into like linear sketching algorithms. So it might be tempting. The first work that came out, again, was this CKN20 paper. It might be tempting to just try to implement their method as a linear sketch, but it actually is much more difficult than just saying like that. In particular, their method relies on something called balanced assignment. And this kind of appeared in Yuichi's talk as well. I think we kind of turn every hyperedge into a clique and like assign these weights to all the constituent edges. And it's a very hard process to implement with a linear sketch. Like we're really unsure how to do that. Thankfully for us, Kent had like a really beautiful work on hypergraph sparsification and in general, like this quotient of submodular function sparsification that we can bootstrap and kind of use as the foundation for the sparsification framework that we build today. So I'll kind of summarize this framework briefly and then talk about some challenges that come up when we try to implement it with a linear sketch. So the main observation of Kent's paper is the kind of this definition of what's sometimes called k-cut strength or sometimes called like the minimum normalized k-cut. And for an analogy, the kind of the motivation of this parameter is that in the graph setting, as we saw in Madhu's talk, if you want to create a sparsifier, you can sample at rate basically 1 over the minimum cut, and this will preserve all the cuts to a multiplicative factor. In a hypergraph, you cannot do this. You can't sample at rate 1 over the minimum cut. But it turns out there is another quantity, exactly this quantity phi that I have on the slide here, which does govern like your ability to uniformly sample hyperedges. So in particular, this parameter, we're taking the vertex at V. We're choosing a number of parts, which we denote by k. Now we split the vertex at V into these k parts. And we look at how many hyperedges are crossing between these parts. So when k equals 2, this is just the same definition as like the ordinary minimum cut. When k equals 3, we're choosing like some v1, v2, v3, and looking, OK, how many hyperedges cross between them? And if it touches all 3 of these components, it still only counts as a single hyperedge that's crossing. And Kent's work showed that given a hypergraph H, and given this parameter phi, you actually can uniformly sample hyperedges at rate basically 1 over this parameter phi, while still getting a cut sparsifier with high probability. So a very natural algorithm then is just define the hypergraph G. That's what we're starting with. And now instead of recovering edges that have like low strength, as we did in the graph setting, let's recover hyperedges whose k-cut strength is less than or equal to this value. And by strength here, all I'm saying is basically keep removing hyperedges until the minimum k cut gets sufficiently large that we can now sample. That's all that strength really intuitively means. And hopefully the correctness of this is clear, because it's really the exact same thing that we did before, except now instead of using Karger, we're just using Kent's work. But this kind of leaves an elephant in the room. How actually do we recover these edges with small k-cut strength in a linear sketch? And I won't be able to go through all the details, but I hope that I'll present a single example where some of the complexities will appear, and will also motivate the key technical tool that we introduced to overcome this challenge. And that's this example. So we have a hypergraph on n vertices. The size of every hyperedge will be square root n. That's to say that arity r is square root n. And we break the vertex set into square root n different parts. Right? So we have v1, v2, v3, v4, all the way up to v square root n. These are like components, each of size square root n. And now within each component, we basically have like a complete hypergraph. So it has like 2 to the square root n vertices. Every possible subset within each of these square root n components is present. And then we also have some hyperedges that are crossing between the parts. So the intuition is that each part itself is a super strong component. They have so many hyperedges, they're very well connected. Meanwhile, between the parts, we have these square root n hyperedges of arity square root n that are kind of the low strength hyperedges. These are going to be the ones that we want to recover. And in particular, so there's square root n parts. Each one of these is of arity square root n. So what this means is that each one of these hyperedges is just taking a single vertex from each part. Right? So if we look at like this v7, one of these red hyperedges is just taking u2. It's only taking a single one of them from each component. And if we go back to Kent's definition, right, we want to find out what is like the minimum k-cut in this hypergraph. It turns out it'll just be theta 1, and it corresponds exactly to this kind of canonical partition. These are the square root n parts we take. The number of hyperedges crossing between them is also square root n. The number of parts it breaks into is square root n. So the minimum normalized k-cut value will be something like square root n divided by square root n minus 1. So we'll just call it theta 1. Either way, if we go back to our algorithm, what we wanted to do was recover all the edges with small k-cut strength. And that includes these hyperedges. Right? We need to recover all of these big crossing hyperedges of arity square root n if we want to use Kent's framework for sparsification. So let's kind of harken back and try to do this. Right? The main tool we have is with spanning forests. Maybe we can use spanning forests built on L0 samplers to recover these crossing hyperedges, these hyperedges of arity square root n that touch all the components. And recall the way this procedure works. For each vertex, we have an L0 sampler that's stored. And in a given round, all of these L0 samplers have the same randomness, because this allows us to add the samplers together and now sample from like the neighborhood of the components we're forming. OK, so in a single round, we open some samplers, we get some new hyperedges. With extremely high probability in this first round, all the hyperedges are contained in one of these components. Right? There's like 2 to the square root n hyperedges in each component, only square root n that are crossing between. Right? So we're basically, with extremely high probability, just going to recover like the component structure v7, or we recover v6. We're not recovering anything that's crossing in between. Right? And now in the next round, we recovered these hyperedges. So we add all the samplers together, corresponding to these components that were uncovered. So what this will look like is that every vertex in v7 will add together the samplers for this component. And this now gives us an L0 sampler for the entire neighborhood of this component v7. Exactly, right? So we found these components vi. Now we've added together their L0 samplers with shared randomness. And now this gives us L0 samplers for kind of the neighborhood of each of these components. So the way I've written this is I have like L0 of the neighborhood of v1, v2, up to v square root n. The big problem, though, is that in order to add these samplers together, we needed to use the same randomness. Right? So here we have R, we have R, we have R. Not only that, we also have that every single neighborhood is exactly the same. Right? Each of one of these square root n hyperedges is touching all square root n of the components. So what does this mean? Gamma v1 equals gamma v2 equals gamma v square root n, everything in between. So we have L0 samplers with the same randomness on the same support. So when we try to recover a hyperedge using these samplers, everyone will report the same single hyperedge. Okay, maybe we'll say, okay, let's try to use different randomness for the different components. But we can't do that because we don't actually know what the components are when we're building our linear sketch. But we have our hands behind our back. We have to use the same randomness on all of the vertices. So it becomes a problem. How do we actually decorrelate these different components and make sure that when we recover hyperedges, we actually recover distinct hyperedges? Because otherwise, we'll be doomed, because in order to recover these square root n crossing hyperedges, we'll need to store at least square root n L0 samplers for each vertex. And this will lead to a quadratic dependence on this parameter r. So this will lead to something like n times square root n squared. And recall, our goal is to get a linear dependence on this arity. And so this is where kind of one of the key techniques in the paper comes about. Yeah. Oh, great question, yeah. So one of the factors is because we're storing square root n per vertex. The other factor is in the actual description complexity of an L0 sampler. It has a dependence on r, because the universe that it's representing has so many more hyperedges. Exactly, but yeah, thanks for clarifying. I should have made that clear. Any other questions? Great. So the solution we use to kind of break this problem, right? So we can't, as a consequence of this question, we can't actually afford to store more than like polylog n L0 samplers for each vertex. So what do? We introduce a notion of fingerprinting. All this means is that for any hyperedge E, we perform like a random independent fingerprint, where this means we keep each vertex of the hyperedge with some probability p. So on the left, right, we have these three hyperedges of square root n, well, really square root n, but I didn't want to make it messy. And now we'd use this fingerprinting rate p, which is like log n over square root n. And we just sample each hyperedge independently. We keep a vertex with this probability. And what happens, so with high probability, there's only like log n vertices that survive in each hyperedge. And what this means is that the VIs can't even share too many of the same hyperedges, right? If an L0 sampler returns some hyperedge E now, it can only log n samplers can return that same hyperedge. Yeah, Roby? Yes, when we
you edit as if it contained only.
Exactly, yeah. So to repeat what he was asking, so is it actually that we only recover the part hyperedge, or we just like we store the fingerprint, but we still have the information. So when we recover the fingerprinted hyperedge, we know that it actually corresponds to this big global hyperedge. Exactly. So we've only kind of broken the correlation in terms of like what the sampler sees, not what it like what we see as a result. But yeah, so now the arity is like order log n. So the VIs don't share too many hyperedges. In particular, in a given round, we'll recover like omega tilde square root n hyperedges. So we only have to store some polylog n L0 samplers for each vertex. And so this is a very idealized example, as you can maybe see. In the general case, it's a bit more complicated. We don't know what the right fingerprinting rate is. In fact, there might even be like multiple fingerprinting rates that you have to try. So what we do is we kind of try a bunch of different values of this fingerprinting rate. We store like spanning forests for all of these different rates. And it turns out through kind of a pretty detailed analysis of this procedure, we can actually save this final factor var and get the linear dependence. And so I know I'm running up on time. It'll be just a couple more minutes. I promised you I'd get rid of all the factors of log m, but we still have 4. So I'll just say very briefly how we get rid of these. So recall one of the factors of log squared m was coming from the fact that we set the epsilon prime parameter to be epsilon over log m. We perform like a much tighter analysis of this kind of resparsification framework, which shows that you can actually set epsilon prime to be like epsilon over log squared n. And this will then save a kind of a factor of log squared m. It replaces with like only log n's and log 1 over epsilons. The second problem deals with the fact that each L0 sampler has a dependence on r, and then also a dependence on the support size of the vector it's representing. Right? So in each graph, you can have m hyperedges. That means that there's necessarily like r log m bits per L0 sampler. So what we do is we kind of show there's a pre-processing phase that you could use, which merges away the super strong components. For instance, like in the previous example that we saw, the pre-processing phase would find these v1 to v squared n and merge them away like beforehand. So now the L0 samplers only have to store like a support size of size square root n, in general some poly n value. And saving the support will save you the final factor of log m. And this gives you the running tally where we have this O tilde nr log m over epsilon squared. The lower bound follows from basically like bootstrapping some of these lower bounds for L0 samplers. And in particular, a lower bound even holds for the setting of just recovering a single like spanning forest of a hypergraph. So in conclusion, right, we implemented a series of like optimizations to optimize the complexity of linear sketches for hypergraph cut sparsification. And the last thing I wanted to mention is that in some more recent work, and kind of inspired by some of the techniques that appeared in this paper, it turns out that we can get many more general algorithms, like in a similar flavor. In particular, this work with Sanjeev and also Juan, who I guess isn't here, we get like near optimal fully dynamic hypergraph cut sparsification. We get near optimal online hypergraph cut sparsification. And we even get near optimal insertion only streaming cut hypergraph, like hypergraph cut sparsification bounds. And this is what the complexities will look like. One thing I'll highlight here, so today was basically the dynamic setting. In the insertion only setting, you can basically save this entire factor of log m and just get it to be like O tilde nr over epsilon squared. And I think I'm already a little bit over time, so I'll leave it at that. And please, if there's any questions, I'm more than happy.
Any questions?
Okay.
Intuitively, why is there a log m in the lower bound?
So it's basically because for an L0 sampler itself, the lower bound is already like r log m. So all we do is we bootstrap, we build a bipartite hypergraph where you have like n over 2 vertices on the left, n over 2 vertices on the right. And now each hyperedge touches a single left vertex and then a bunch of things on the right. So you're basically simulating like n over 2 L0 samplers, and for each one you have an r log m lower bound. Does that answer your question? Yeah. Okay. Yeah, go ahead.
Was this for also weighted hypergraphs?
So it depends on the notion of weighting that you do. So there's kind of a canonical way to turn these linear sketches into weighted examples where like you can insert a hyperedge with weight 10 and you can delete the hyperedge with weight 10. There's a more complicated model where you have like a single hyperedge and then you increase the weight by 1, increase it by 1 again, subtract the weight by 2. So you're not like inserting the same copy, you're just updating the weight continuously. That setting we don't solve. It's called like the turnstile setting. That's a bit more involved.
And in the weighted setting, does like log m become log of total weights or anything like that?
Yes, we break it into like probably log base like 1 plus epsilon of W weight classes. So I would imagine it's that. Yeah, exactly. Zephyr?
Streaming algorithm, is it some merge and reduce type result, or and then you can apply this better analysis of error you have? Or?
Yeah, that's yeah, pretty much. Yeah.
Got me thinking, you cannot handle division in linear sketching. You go up about what you described. It's a linear sketch.
Yeah.
It's usually very effective for division because it's a linear sketch.
Yeah.
But your step of like sampling log n out of root n in your example, sampling log n out of root n, it means that you have to, if you want to delete it, you have to know which log n you sampled.
Yeah. Yeah, so you're right. There's like a de-randomization question, I guess is what you're saying. Basically, you want to know what the randomness you used to fingerprint it was. Yeah, so he's right. So if you want to delete a hyperedge that was inserted, you have to know, okay, what was the fingerprint we used for that hyperedge? And so we just solve this by basically creating a non-uniform streaming algorithm. Right, so you can, and then you can, it's like hardwired like into the description. Because yeah, yeah.
Any more questions? If not, then it's lunchtime. Thank you.
Yeah, thank you.